Good morning, Ron. Hi.
Good morning. How are you?
Yes,
Okay,
I'm fine.
it's tested. Okay.
How are you?
Okay.
Thank God.
Okay. Alhamdulillah.
What's the right translation for Baruch Hashem?
Thank God.
Thank
Yeah.
God. Okay.
Let's
Um,
be the God. Thank
I
God.
know you and God are very close.
Yes, yes.
Uh,
I'm taking
last
care of it.
time, last time we ran into some numerical issues, and
Yeah. Did you solve
let,
it?
let, yeah, it was just a really idiotic bug. As many times. This profession of being a programmer
Mm-hmm.
is a combination of tedious work and inspiration, I would say.
Yeah. When I did it for a year or two in my life when I was 20. And I liked it. I liked the debugging part.
Really, you like the debugging part? Because I like
Yeah,
having a general tool that enables me to create, to be a magician, but I
yeah,
do not like the
it's
debugging
also,
part.
yeah, it's like solving riddles, solving puzzles.
Ah, you like the detective part of
Yes,
asking
yes.
the right question
I
to
like
find the
being
truth.
absorbed into the program. Namely, the program is much more important than me. It's a good feeling that you're not important. It's, the program is
Okay,
important.
let me share my screen. Uh, that was deep. Um, where were we? Okay, so this is our code here. We were dealing with, that's the table of contents. I'm jumping into the train part. We were talking about the definition of F. What is F? Let, let us remind ourselves what is the meaning of F.
So the main thing is what is the dimension of the image of, yes, it's 2
Uh,
by
why is
200.
this the main thing? It's important, but
So if you know the dimensions, you understand what it does. So
Mm,
it's 2 by 200. Let's say, yeah, you agree
right.
with me?
Yeah, right.
Okay.
It's 2 by
So
200.
it takes the
So,
current W, current parameters,
mhm, mhm.
and for every cat or dog, for every image, it gives you some vector, 2 by 1 vector. Yes,
Yeah,
2 by 1
a
vector.
probability vector of binary
Vector
probability,
that
right?
tells you what do you think of life? Do you think it's a cat, life is a cat, or do you think life is a dog? Okay.
Right. We can call it a
With probability.
prediction. A prediction
Yes,
whether it's
okay.
a dog or a cat, and the values can be considered as a confidence level also, right?
Yes.
Okay.
Mm-hmm.
This is the meaning of F, and F is our approximation for the real unknown function we are trying to approximate. Also, F is called the neuron, artificial neuron network. But
Mm-hmm.
we actually didn't talk about it, why we call it, why they call it like that. In all this course, we kind of avoided all this attitude of neural network, but we'll get into it later. But
Okay.
I'm just saying it now. So this is F, and it was extremely simple, right? It had this linear part, which is just a matrix multiplication between W and X, and
Mm-hmm.
uh, and then what was it? You
Softmax.
remember why we did this, line 3 here?
No, logit is just the name of the thing, but
Yeah, logit
when you
is
say
just the name of,
logit.max is softmax, that's what you're saying?
it's before the softmax. Logit is the name we gave the result
Later.
of the matrix multiplication. But Line 3 was a result of a numerical problem we ran into. You remember? This line subtract the maximum value.
Yes, yes. So as to make it within normal range.
Exactly,
So it will
because
not be
we are
crazy.
going to, exactly, we're going to apply exponent, and if it's too high a value, it will overflow. So we did that, and then these two lines are actually the softmax.
Softmax.
Exponent and normalization.
Yes.
Okay. Now, we in the end of the last lesson, we ran into a numerical issue that was a surprise for me, but it was just a bug. Actually, I used here a data set, and I should have used this, sorry. Our data set is in this variable. We call it, and data set was a different thing. It was just a bug. So I will run it again, okay, with the right. DS is our data set, all the examples. I will run it. It was just a bug. So now, instead of showing F, let's show F transpose. It will be easier to see. So F is our prediction.
What are these ones? I don't understand. Ones and zero.
It's kind of funny that it's deterministic distributions, right?
Yes,
We
yes.
we were expecting a relaxed version of it, but it's after softmax. Softmax is
So you took E2 there, so it was huge numbers or very small numbers.
Okay. You see here, that's actually a zero, practically zero.
That's so you zerify all those small numbers.
So but I would expect sometimes a real distribution, like not deterministic one, but everything here seems to be
Didn't get it.
deterministic.
267 is a huge number. E to the 267.
Pardon? I didn't get that. What
There
was
was
that?
a line with E to the minus 267.
Yeah, it's practically zero,
It's zero.
right?
So so you never got there any number that is non-zero.
Everything is funny. I think this is a very small number, but it's still practically zero. Maybe if we'll run it again, we'll get some other. It starts with a randomic W, right? So if I run it again, wow, now it's completely
Deterministic. Yes.
okay. But it seems to be working. Let's continue.
Let's see if it recognizes cats and dogs. Let's see.
Let's see if it gives us if it learns how. But before that, I know of another issue, of a numerical issue. Let's fix it also. The other issue that I know of is in the loss function. Log. Let's do it. Just a minute. I will. This is the cell in which we are making our experiment. I will move it down under the loss function. Just a minute. Let me arrange so we'll have more space. Okay. Have a look. This is our implementation of the loss function. Do you remember what the loss function does?
Yeah, how far you are from the truth? Yes, from.
Yeah, from the function we are trying to approximate.
The thing that the trainer gives you. Yes.
Right.
So the trainer tells you deterministically, this is a dog, this is a cat.
Right. But what was our criteria for distance?
The Kullback library distance between.
That's true. It's equivalent, but we called it cross entropy. It's equivalent in this case.
Yes. Okay. Yes.
Yeah.
Okay.
And here I just wrote it as a reminder. We are looking for this is Y and this is F. Y is our original tagging, right? It's 1 and 0, right? This is Y. It's 200 here, right? It's 200.
Yes.
200 samples, and this is the right, let's call it labeling, right? It's labeling. Sorry for the handwriting. Labeling. And what is F? F is our prediction, right? So it's in the same size, but it's supposed to be real distribution, like not only deterministic one.
Okay.
This is a prediction.
Although in your case, it is deterministic by mistake.
In our example, it was deterministic,
Yes.
but it shouldn't be only deterministic. Predictions. I'm writing with the mouse, sorry. Predict. Okay, predict. Okay, so this is the definition of cross entropy here for a single, if I'll take two distribution, this distribution here and this distribution here, and I want to know the cross entropy between them. This is one notation, and this is an equivalent notation, which I think it's better because it's symmetric. So the distance between Y and F is defined as follows: minus first element of 1 multiplied by log. This is log in base 2. Remember?
Yes.
Log in base 2. So this is a definition. And because Y is a deterministic distribution, one of them will be 0 and the other one will be 1, right?
Yes.
So eventually it will only look like log, the value will be log of the right element of F. Let's say it's, I don't know, it's one of them, either 1 or 2, but that's it. Yeah, okay, that will be, okay. And when we program it, we had a numerical issue. What did we do? First, we applied F in order to know our prediction, okay? And then, what is this line here? What did we do here?
This is the cross entropy. What do you mean? 1 minute.
The sign of multiplication, what kind of multiplication is that?
That's what's called Hadamard multiplication, point by point.
That's element-wise multiplication, not matrix multiplication.
Yes, point by point.
You remember that F and the Y have the same dimensions, right?
Yes. Okay.
So this here is after applying a log in base 2 of all the element of F. And this is element-wise multiplication with Y. So it makes sense, right? So if we'll go back to here, so we multiplied 1 by log of 0.8, we multiply 0 by
and the Kullback-Leibler distance is just the sum of all these guys.
Yeah, the sum of them with minus. Yeah.
Yes.
But there is a numerical issue. Suppose this Y is 0 and this log 2 is also 0. Like, suppose we have 0 here and here. So 0 multiplied by anything is 0, right? But log of 0 is actually minus infinity, right?
Infinity, yes.
But we have an issue with this library. Let's have a look. NP log in base 2 of 0.
This he will shout at you. He will yell at you.
It told me it's minus infinity, which is correct, right?
Mhm.
But he issued a warning.
Mhm.
Divide by 0. I guess he divided by 0 because of converting bases
Okay.
with the formula of conversion. But I want to avoid that, okay? I don't want to multiply. If this is 0, I don't want to multiply. I want it to be just 0, okay?
Sure. Okay.
So let's make it, let's make the calculation in a different way. And during that, we'll learn something about the library, which is very useful. So have a look. I will write an example. Y will be an example of a matrix of Y, but small one, just an artificial small one. So NP array, I will write it like that. 1, 0, 0, 0, 1, 1. Makes sense.
Mhm.
Let's try.
Yes,
This
yes.
is Y. Y should be a labeling function, right? So it should
You wrote it.
look
Yeah.
like that, right? What?
Yeah. You now wrote
Okay.
it as a matrix. Great. Okay.
Now let's make an artificial F with the same size with different numbers. So let's say it's minus, and this should be 2, right? Here I will add like, let's print it, Y and F. So the first matrix is labeling and the other one is a prediction. So it makes sense, right? Prediction should sum to 1, right?
Okay.
Okay, so now I want a calculation that takes into account only the places that Y has 1s, right? I don't want to mess with all these places because I know they are 0 anyway, right?
Mm-hmm.
So I will first show you that I can write something like this. What do you think it will do? When I say 1, you remember what's the meaning of equal sign?
Definition.
Pardon?
It's Y is defined as.
No, one equation sign actually means assignment. Put
Yeah.
this value into this value.
Yes.
But two equation sign had a completely different meaning. We use it in condition, like if A equals 7, do something.
Uh-huh.
It's a condition, right?
Yes. Okay.
Okay, so what does it mean to put a matrix into in a condition? It actually has a meaning of producing a new matrix with Boolean value. Let me show you. You see this true, false, false, false. I will put Y before in order for you to see.
Yeah.
So I will print Y and Y equals 1. You see
Uh-huh.
what happens?
Yeah. So you got a logical matrix. Okay.
Yeah, we
Boolean
have a
matrix.
Boolean matrix with true in entries that satisfy the condition and false in entries that doesn't satisfy the condition. Okay.
Mm-hmm.
And now I will do another thing that will seems weird to you, I think. I will talk about f in the place. This seems weird, right?
Yes. Okay. So F, you apply it only.
We did when before we did something like that. This is the element in row zero.
It's going to
And
be a vector. What is this?
okay.
What does it denote?
Okay.
Vector?
Let me do it in two steps. I'll put this as a remark. What does that mean? This is the element in a specific place in the matrix. I don't want us to be confused. I will write F and have a look. First, I printed F, and then I printed F in place 0, 1. 0, 1 is actually this element here. For us, this was a way to address a specific entry in a matrix.
Okay. Yes. Okay. Okay.
Okay.
When
So
the labeling starts from 0. Okay.
yeah, all the indexing starts from 0. But now I want to do other thing. Instead of specifying a specific place as an index, I put a Boolean matrix like that, which is weird, right?
All the places that it's true for it. So
yeah. I will print.
In this case, only one element. So 1, 1, 1, right?
Let's have a look. First, I printed this Boolean matrix with true in places of 1 and false in places of 0.
Okay.
Then I printed F, which is the prediction matrix. And what is this here? What happened here? So I asked for the matrix only in places of true.
Which gives you a vector. Yes. Okay.
Which gives me, a vector with one dimension.
Yes.
Coming to think about it, what would have happened if I have 2 and 2 here? What would have happened? Let me try.
One of the places it will have 2 places. 2. You're going to get 4 numbers.
I want to run an experiment. Just a minute. I'll have another matrix which equals this, and I'll put it, and then I'll put M in the place of 1, 0. I want to change it into true, and then I want to what I did now is just change this value into true and wanted to see what happens. Okay, you understand?
Yes. Okay.
I don't know what will happen. Let me see. Oh, he added it to. It's still a vector with one dimension, but he added these 2 values.
Okay.
But it will never happen to us because why?
You have only 1, 0 or 0, 1. Yes.
Yeah, exactly. So we are fine. I'll delete this. I'll delete everything we did here, and I will just talk about F and F in so let's have a look. Y is the labeling, F is a prediction, and here are only the value of F that corresponds to places that had one, right? That's exactly what we want, right?
Yes, yes.
Okay, so let's use this in order to make a simpler implementation. So I will delete those two lines here because I'm going to implement it in a different way. And I will just return the following. Minus, I have to remember I need to do minus, and I will do f in place y equal 1. I want to sum this up, and I want to divide it by k because let's understand what I did here. So after we do, I forgot something important. Sorry. I forgot log 2 of that. Let's see what I did here. So what is f in the place of y equal 1? It's the places of f that are actually important for me, right?
For me, it's clear, so you don't have to elaborate too much now. Only that in the Kullback library, you do eventually the average of these guys, yes? In the cross entropy.
Yeah.
Each of them.
But, yeah, this is the sum of all the logs, the relevant logs. This is the minus sign which was determined by the definition of cross entropy. Why did I divide it by k?
I think that's one of the parameters. In the definition of the cross entropy, you do that because why do you do that? No.
Yeah, k is the number of samples. It's 200. Yes. We wanted an average on the cross entropy.
Average, yes.
Yeah, it's just an average. So I think we're fine now. I will redefine it as, okay. So now maybe we can try to run the code. What do you say?
It's up to you.
And hope for the best. So are you ready? It's a historic moment. So this is train. In order to run it, we need this line here, train on DS. Let's do it.
What does the program produce?
We should see a training process, an iteration of gradient descent that show us improvements in this stage.
So at each step, you get a W for that step, for that stage. How do you test this W?
Okay. Let's see again what code are we running. We had a function called train. We start with X and Y, our data. W start with an arbitrary value that we randomize. And then we have a loop over epochs. In each epoch, we calculate the gradient of W. We update the value of W with the gradient multiplied by the learning rate, which is the size of the step. And we calculate the loss. And occasionally, we display the loss and the epoch just for the user to see the improvement. Make sense?
Yes, but what do you want? You want the loss to be 0 or what?
I want the loss
to be how do you test success?
I want the loss to be minimal, and if the training process will be good, eventually it will stabilize and will not improve much. And I would
Then
like
you'll have
the
to
loss
test
to
it
be zero.
on images. Yes.
Pardon?
And then you have to test it on images to see if
Exactly, exactly. Then I will, all I want from this process is the W which he will come up with, and then I will test this W whether it's doing a good prediction on new images that he didn't see. Okay, let's see. I'm not very optimistic. Okay, we still have runtime divided by zero, but I'm not surprised because sometimes we have 1 multiplied by a log of 0. So I don't really mind this error because minus infinity is the right answer. But now I see it takes a long time, and I don't see any progress, which is not very good. So I will stop this process here because I don't see any printing. The next thing I would like to check is whether the numerical calculation of the gradient takes a long time. But I think that's a good time to stop, and we'll continue next time.
Okay, check it.
Okay?
Yes.
So thank you,
Okay.
Ron.
See you. Bye-bye.
Bye-bye. The best.
Ori?
Yeah, just a minute. I'm stopping just a minute.